Let us now try and derive a second form of Bloch's theorem. And in order to do so, let's be a little bit creative and define a certain function u of z. And we're going to define that as the product of a Bloch mode, h of z, and an exponential plus j kz z. Okay, so that's just an idea we have. Let's define a function like this. And then the question is, we can wonder, this function u of z, given the fact that h of z is a Bloch mode, will this actually be a periodic function? So if you calculate u of z plus an integer multiple times the period a, will you end up back with u of z? So that's an interesting question, and you can pause the video and see if this is the case or not. Okay, let's calculate u of z plus LA. So this means that we have exponential j kz, and then we have z replaced by z plus LA. So this is going to give us a product of two exponentials, exponential j kz LA, right? And then we have h of z plus LA. So this is just in the definition replacing z by z plus LA. But let's not forget, this h here is a Bloch mode, so we can apply Bloch's theorem. And Bloch's theorem tells us that h of z plus LA, if we relate that to h of z, that we basically have h of z times exponential minus j kz LA. So if we combine this information from Bloch's theorem with what we had earlier, then these two things cancel, exponential minus and exponential plus j kz LA. And in the end, we can write that this is equal to exponential j kz z h of z. And if we then refer back to our definition, this is actually indeed u of z. So now what we've shown is that this function u that we've defined actually has the same periodicity as the lattice. Okay, now it's just a matter of taking that equation here and reformulating this a little bit to bring h of z to the left-hand side. Now we can write that if we have a Bloch mode h of z, that you can actually write this as exponential minus j kz z times a function u of z, a function u of z which is periodic with the same periods of the lattice. So u of z plus LA is u of z. And this actually is the second form of Bloch's theorem. And if you look at what this means, this basically tells you that if you have a solution to Maxwell's equations in periodic media, a Bloch mode h of z, that actually you can write this as a product of two parts. Namely, on the one hand, we have a periodic function, u of z, the same periodicity as the lattice. And then on the other hand, this plane wave, exponential minus j kz. So again, this shows that a Bloch mode itself is not periodic, but it's the product of a periodic function times a plane wave. And there's actually a special name for this combination, for this product. This is what people sometimes call a pseudo-periodic function. Okay, so this is the second form of Bloch's theorem, which allows you basically to gain additional insight into what the Bloch mode actually is, a product of a plane wave with a periodic function. And in order to expand on this theme a little bit, let's make use of the fact that u of z is a periodic function. And of course, if you're confronted with a periodic function, you have this natural urge to try and express this in a Fourier series. And I suggest you pause the video and you do exactly that. And you write u of z as a sum. Well, rather than writing it as a sum of sines and cosines, I would write it as a sum of complex exponentials to stay a little bit in the same vein of the formulas that we've been using so far. So pause the video, write u as a Fourier series, and see what that means for the Bloch mode h of z itself. Okay, our Fourier series basically looks something like this. We have a sum over m going from minus infinity to plus infinity of complex exponentials, aka plane waves, exponential minus j, and then we have m 2 pi over a times z. And then each of these plane waves has their own expansion coefficient, u of m. So this is just from basic Fourier theory, the way you write a periodic function as a sum of complex valued exponentials. Now, substituting this form into the second form of Bloch's theorem above, that basically allows us to write h of z also as a sum of plane waves. The only thing we need to do is, if you look at the formula again, is multiply everything by exponential minus j kz. So then we can write that our Bloch mode is a sum from m going from minus infinity to plus infinity, some expansion coefficients um, and then exponential minus kz, our Bloch mode vector, and then multiples 2 pi over a times z. So this gives us yet another way of looking at the Bloch mode. So pause the video and try and interpret what we've written down here. And perhaps you can also find a relationship between this thing and the Brillouin zone that we've introduced in the last video. If you look at this equation, this basically tells you that a Bloch mode is an infinite sum of these guys, and these complex exponentials, as was mentioned before, they are in fact plane waves. So a Bloch mode can be considered as a sum of an infinite number of plane waves. And the interesting part is that the wave vectors of these plane waves, as you see here, they basically form a family kz plus integer multiples of 2 pi over a. So if you want to represent your Bloch mode with just a single one of these wave vectors, then it basically doesn't matter which of this infinite family that you pick. If you just pick one wave vector, you can recover all the other wave vectors by adding integer multiples of 2 pi over a. And that's just basically the same argument that we had previously with the Brillouin zones, where we also restricted the k values to a non-redundant region of size 2 pi over a. So remember, from minus pi over a to pi over a. So it doesn't really matter which k vector you pick to represent the Bloch mode. Of course, each of these infinite numbers of plane waves has its own different expansion coefficient um, but that's basically the information that's also contained in this modulating function u of z. Okay, so here we have it, the second form of Bloch's theorem, which hopefully gives us a little bit more insight into what exactly these Bloch modes are.